Hi. We have to move elements of a numeric vector that have a certain value to the front of that vector. A traditional way to do this in APL is to use sorting, but not sorting the vector itself, that wouldn't work. Rather, sorting by a certain criteria. Let's have a little lambda here and compare the left argument to the right argument. Now we have indication of where the 3's are. And if we were to sort so all the zeros came first, well, all the numbers that correspond to zeros, then we would have all the 3's at the rear. Let's flip the 1's and 0's by using unequal instead. Now, if we were to sort such that the numbers corresponding to zeros came first, then the 3's would come first. How can we do that? The grade function gives us the indices that we would need to select elements from such that the argument would be sorted. This says, in order to sort this numeric vector, we need to get element number 3 first, that's the 0. Then element number 6, that's the other 0. And then 1, 2, 4, 5, and so on, all the 1's. Of course, we don't want to sort the Boolean vector. We want to sort the corresponding numbers in the actual data vector. But this will still work, because the third element is a 3, and the sixth element is a 3, and then comes element number 1, 2, 4, and so on. So, instead of reordering the Boolean vector, we are reordering the right argument. This indexing square bracket can take multiple indices, and then we just get all the elements selected by those indices. And this solves the problem using grading and reordering based on that grade. This might seem like a very neat little solution, but there's actually something even shorter, and I like this one better. And that's using set functions. Let's think of these two arguments here as sets. What we want to do is to find the intersection of these sets. That would be those two 3's. And the set difference, that's all the other elements. If we can then put together the intersection and the set difference after each other, then we have solved the problem. And this isn't very hard. Let's start with the set difference. For that, we use the without function. You can hear the name that it takes the data on the left without the data on the right, which is the opposite of what we want. Luckily, we have the higher order function, or monadic operator, which can flip the arguments of these two functions. Flip the arguments of this function. So here are all the numbers from the right except the numbers from the left, or without the numbers on the left. There's only one number, but it can still be seen as a set. Similarly, we can take the intersection. That's those two 3's. Notice how this deals with kind of multi-sets, and that we're allowed to have duplicates. And that's exactly what we want here. Okay, then we just need this intersection followed by the set difference. And that solves the problem as well. Note how we are commuting both of these outer functions, and this is actually a fork construct. This means that the outer functions, these two, are applied to the arguments, and then the results are combined using the concatenation function. We could also just flip the arguments of the outer function, and then the inner functions wouldn't need to flip so much. Another thing we could do, but that doesn't really make a difference, is to replace the concatenation with a union, being that the intersection and the set difference cannot share any elements, then that's effectively a concatenation. It's just kind of cute that we are only using set functions to solve this problem. Thank you for watching.